Yeah, good morning and welcome to our today's lesson. We are still on laws of motion, that is Newton's laws of motion. We looked at two of them, where we had the first one. Just to bring you up to speed, the first law of motion states that a body remains in its state of motion unless acted upon by an external force. Now, we were able to establish that bodies have that natural reluctance to change in their state of motion. Therefore, we considered a few factors in that case. We looked at momentum, whereby now we now brought in the aspect of velocity. We also related the mass and subsequently the force that acts on these bodies. Now, depending on the mass of the bodies, the force required to change the state of motion is informed by the mass of the body, and the force is responsible for bringing about a velocity in a given direction. Therefore, we were able to say that momentum, which we abbreviated as P, is equal to mass, which we called M, and this one we multiplied by the velocity, V. It's always important to recall that mass of a body is actually constant everywhere, but velocity can change now depending on the magnitude of the force that acts on our body. Now, we also pointed out that velocity has a direction in itself because it is actually a vector, and therefore our momentum is going to assume the direction of the velocity, and for that reason we classify momentum as a vector. Now we also came to law number 2. And now law number 2 now talks about the force that we are talking about and the result of the force. We were able to rope in the aspect of impulse, whereby a force acts very fast and the results thereof are therefore realized equally fast. And we were able to relate momentum and the impulse, and we were able to find out that the two are related in the fact that the impulse of a force is equal to change in momentum. Impulse, which was given by force, the external force, and the time it takes to impact on the body, was equal to the change, because we said if the body was at rest, having introduced an external force, then you expect some motion to result. If it was in motion, it could either be accelerated or even halted. In both cases, we can take care of that and equate it to impulse. Now, mass of a body is constant everywhere. Mass is constant everywhere, and therefore, for you to change the momentum, the only aspect that can be changed is actually velocity, because the mass is constant everywhere. Now today we will consider the third law of momentum and the third law of motion, sorry. And when we talk about the third law of motion, again we consider the forces that act on a body, and it's important to note that the force or the forces that act on a body are actually coupled. By that I mean that action force will always yearn for a reaction force. Now, for a body to remain at rest, we want the net forces acting on the body to be 0. Therefore, if we considered a block of wood, for example, resting on a surface, and by virtue of it having some mass, it will have some weight that is going to act downwards. This weight is equal to mass and the gravitational acceleration or the gravitation pull multiplied together. Now, equally, when the block now exerts this force on this surface, the surface equally exerts another force upward, which we call the reaction force. Now, for the body to remain at rest, action, which is our weight that is moving downwards, or the one that is pulling the body downwards, and the reaction force, which is the force that is out to counteract the effect of weight, are supposed to balance out. Now, for that reason, we say that action force is equal to negative of reaction force. Action is the negative of reaction force. By that I mean, suppose, for example, we give this one a figure of 20 newtons, for example. 20 newtons, and in this direction that we are calling the downward direction. Now, we take that to be positive because we said a force is actually a vector. Therefore, direction is very important. Now, for our system to remain at rest, reaction should actually be negative 20 newtons. Now, negative because it acts in the opposite direction. Negative because it acts in the opposite direction. Therefore, in writing, we could write that the third row states that action and reaction force or forces are equal in magnitude but opposite in direction. That action and reaction forces are equal in magnitude but opposite in direction. Now, having walked through this journey of forces together, now you can manage to give a reason as to why we say the two forces are actually not equal, because their direction is much as the magnitude is the same, the direction makes them different. You could also write in terms of, the law in terms of momentum, as we are going to observe. But for now, I want us to consider a case of a body in a lift, for example, a body in a lift. Now, the lift is the elevator that we use in tall buildings to ease our task of climbing the stairs. Now, if we consider a body or even a person, or let us consider a passenger in a lift, and let us consider a passenger in a lift or the elevator and give the passenger a mass m. Now, when you step on the elevator, your weight is going to change depending on the acceleration of the elevator and the direction of motion of the elevator. That the passenger experiences forces depending on direction of motion, as well as the acceleration of the lift. Now, I want us to consider the lift at rest. At rest. Now, when the lift is at rest, it means that the passenger is also at rest. If the lift moves upwards, you equally move upward with the same velocity as that of the elevator, and the same case applies when it is moving downwards. But for this case, we want to consider the passenger at rest. When the passenger is actually at rest, the only forces acting on our passenger will be the action action and reaction. Action force and reaction force will be the only two forces that will be acting on our passenger. Now, action force is as a result of the weight and the gravitational acceleration. So this one will be equal to mass times gravitational acceleration. Now the reaction will be equal but opposite in direction to our action force. Therefore, it will be equal to negative mass times g. So while this one is given by mg, this other one is given by negative mg. And when the two cancel each other, our passenger remains at rest. Therefore, his weight is going to be his actual weight. Should you have a weight balance in the lift, it will read mg, the actual weight of our passenger. Now, how about a lift moving upwards? How about lift moving upwards? With now, the lift could also be moving upwards. Now, remember we said when the passenger entered into the elevator, he was at rest. There has to be a net force that has actually accelerated the elevator upwards, so that now our state of inertia is offset. Now, this acceleration here, and you multiply by mass, gives the force, the additional force that actually produces the upward acceleration. So what we want to say, there has to be the force MA and there has to be the force mg, which is actually the weight. Now we have introduced a force ma to offset our balance. But now our weight is also acting downwards. Therefore, the net force, because we said that there is a reaction force which cancels the effect of the weight. Now, the resultant force that will be provided by our additional force that we have given is what is going to propel our elevator upwards. And now the net force will be upward force, and this one we subtract the weight. Upward force, you subtract the weight. Now let us call our upward force force P. Force P. Of course, our weight is mg. Now, the resultant force that is causing upward motion is our ma. Our ma is the force that we have introduced, because were it not for it, now the balance would not have been offset because weight was equal to the reaction. The force that we have introduced is ma, which has been actually resulted from the acceleration of the elevator. And remember the second law of motion. Now, P is the total force or the total reading of our balance in the elevator, and therefore we call it apparent weight. Apparent weight. That on our elevator we have a weighing balance. The weighing balance is not going to read just the weight. It is going to read, because it reads the forces, the magnitude of forces. It is going to read a force that will be an equivalent of our weight and our force that is causing upward acceleration. That is why we call it apparent, because it is not actually the real weight, but the force experienced because of that upward motion. Therefore, the reading of the balance will be equal to apparent weight. Apparent weight, which we are calling P. Now, from the equation that we have just formulated, we have said that net force is equal to apparent weight and we subtract the weight. That net force is apparent weight, you subtract the weight. Now this one we have seen, it's given by mass of our passenger. You multiply by the upward acceleration of the elevator, is given by apparent weight, you subtract the real weight. Apparent weight subtract the real weight. Therefore, if we call this equation 1, then from equation 1, then apparent weight is going to be given by mg plus ma. Apparent weight is going to be given by mg plus ma. Mg plus ma. Now, we can decide to factor out m so that we are left with g plus a. And this is actually what our balance is going to read. G, you add to A, and that one you multiply by the mass of the passenger is going to give you the reading of the balance in the elevator. Now, the lift could also be moving downwards with the same acceleration A. Now, in this case, we said when we are at rest, only two forces act on this body, where we have mg, and then we have another one we are calling the reaction. Again, we have introduced another force to offset the balance, this time in the downwards direction. That we have introduced another force downwards to offset our balance. Therefore, it means that our acceleration is actually negative. Our acceleration must be negative for our elevator to move downwards. Therefore, our net force is given by weight minus apparent weight. Our net force is given by weight minus apparent weight. Where now our apparent weight is therefore going to be, or we can substitute in the equation, MA is given by mg minus, now let us add an apostrophe just to make the difference in directions actually between apparent weight of an elevator moving upwards and that one of an elevator moving downwards. Now, making the apparent weight the subject, making it the subject, you will have apparent weight being equal to mg minus ma. Therefore, instead we can factor out m, so that now m is equal to, apparent weight is equal to m into g minus a. So in other words, we are saying, should you be standing in the elevator and decide to move downwards and determine your weight while the elevator is moving downwards, you are actually going to experience some weightlessness as a result of acceleration of the elevator. Now, we can take some examples to that effect. Let us consider some numeric examples. Now, the question reads that a body of mass 4 kgs hangs or is attached to the hook of a spring balance hanging from the roof of a lift. Now, we are supposed to get the reading of the spring balance when the lift ascends at an acceleration of 0.3 meters per second. That a body of mass 4 kgs is attached. A body of mass 4 kgs is attached to the hook of a spring balance hanging from the roof of a lift. Now, we are required by the question to get the reading of the spring balance when the body ascends at an acceleration of 0.3 meters per second squared. Meters per second squared. This one is a case of upward motion where our apparent weight is given by mass into A plus G. Mass into A plus G. Our mass was given by 4 kgs. Our acceleration has been given as 0.3 meters per second squared. And of course, G is 10 newtons per kgs, or 10 meters per second squared. Let us work out the brackets. Now we have 4 into 0.3 plus 10. That one will give us 4 into 10.3. 4 into 10.3 which gives us 41.2. 41.2, but again, this is a spring balance. Therefore, the units should be given in newtons. In newtons. Now, we also look at the second part of the question. The second part of the question. What is the reading when the lift descends? When the lift descends at an acceleration of 0.2 meters per second squared. Again, go back to your question. Find out in which direction is your elevator moving. And here we are told it is descending. Therefore, this one is a case of downward motion. Now, the elevator is moving downwards and its acceleration is actually 0.2. Now, we are required to get the apparent weight. we are required to get the apparent weight, and we said that when we are moving downwards, apparent weight is given by mass into G minus A. Now, in our case, mass has been given as 4 kgs. G is 10 meters per second squared. You could also give it in newtons per kg. And our A is given by 0.2 meters per second squared. Now, let us substitute in our equation the values of our variables, and this one will yield 4 kgs into 10 meters per second squared minus that is 4 kgs into 10 newtons per kg, and we subtract A, which is 0.2 meters per second squared. Remember, G can also be taken to be acceleration. Therefore, it could be given in newtons per kilogram or even in meters per second squared. So the units need not worry you. Therefore, this one will give us 10 minus 0.2, and this one is 9.8. And our reading therefore becomes 39.2 newtons. 39.2 newtons. We still have one more question. Part C. Part C of the question, we are expected to find the reading on the balance when the lift moves upwards, with constant velocity. When the lift is moving upwards is very key in our question because it determines the equation that we are going to apply. Remember, we could have 3 equations. One is the real weight when the lift is at rest. We also have a case when the lift is moving upwards, and equally when the lift is moving downwards. Now, here we look at what the question has provided. We have the mass, which is 4 kilograms. We have the gravitational acceleration, G, which is 10 meters per second squared. Then we also have A, which is 0 meters per second squared. Now, why 0? 0 because we have been told that the velocity is constant. Constant means that the velocity does not change with time. The velocity is actually constant. But now, our apparent weight is given by mass into G minus A. We have our parameters ready. We can put them in our equations. And 4 for mass, 10 for G, and 0 for A, which means that our apparent weight is going to be 40 newtons. 40 newtons. 40 newtons. Now, I would also want us to look at another example. Example 2. Now, the question reads, a girl of mass 50 kgs stands inside a lift which is ascending at an acceleration of 2 meters per second squared. We are required to determine the reaction of the lift at the feet of our girl. Now, the reaction is actually the apparent weight. The reaction is actually our apparent weight. And remember that we are told it is ascending. Ascending. Then we have been given some rate or some acceleration, which means we cannot just assume A to be 0 because we have been given as 2 meters per second. Now, the apparent weight now will be given by remember this is upward motion, therefore apparent weight is given by mass into G plus A. Now, do we have our parameters from the question? Yes, our mass is 50 kgs. Our G is 10 newtons per kg, and A is 2 meters per second squared. Now, what we are required to do is to feed in the figures of our parameters in the equation that we have so that we can come up with a figure of our interest. Now, mass is 50 and G is 10. Our acceleration is 2. Therefore, 50 into 12. And all these, remember, are newtons, because here we are actually dealing with forces. Now, this gives us 600 newtons. That one will be the reading of our balance. And equally, we said it is also equal to the reaction, because in your mind, you always remember that action and reaction are equal but opposite. Action and reaction are always equal but opposite. This means, much as the lift is moving upwards, there will be that provision of the reaction which is meant to counteract the effect so that the passenger does not topple. Remember, you're just standing. You need the balance. Therefore, you will have to create a balance in relation to the force that you have introduced. Therefore, if you should be asked for the reaction on the feet, that should not worry you, because the action will always be equal to the reaction force. Note that the force that we have gotten here is greater than the weight of the girl, than the weight of the passenger, because of that acceleration we discussed. And we said, for there to be an offset in the balance, or for there to be a change in the state of motion of a body, there has to be an external force. And the direction in which we are going to move is informed by the direction of the external force that we actually introduce. Therefore, action and reaction are equal but opposite. Opposite because of the sense of direction. Now, let us look at the last bit of that question. Let us look at the last bit of that question. The last bit of the question. And the question, part B, reads, suppose the girl decides to descend in the lift, accelerated at 3 meters per second, what would be the reaction? What would be the reaction? Now, so much literature to guide us on the direction of the motion of the girl with her lift, that she is descending. She is moving downwards, and the elevator or the lift has been accelerated at 3 meters per second. Her mass remains 50 kgs. Now, her acceleration now becomes 3 meters per second but downwards, and now G is also constant at 10 newtons per kg. Therefore, our apparent weight is going to be given by mass into G minus A, which is going to be mass into 10 minus 3, which will be 50 into 7, which gives us 350 newtons. Again, if you consider the reading of the lift and compare it to the actual weight of the girl, you see that she actually experiences some weightlessness as a result of direction of motion of the lift. Therefore, we have been able to establish that depending on direction of motion and the acceleration of a lift, you could experience an increase in your weight or even weightlessness as you continue in your elevator. You could experience weightlessness or even your weight could increase depending on acceleration and the direction of motion. That's all for today. I wish you well. Next time we meet, we are going to look at laws of conservation of linear momentum. Thank you.